Welcome back to our second section of fluid mechanics. This is where we start to have fluids in motion, and the chapter is called Flow of Fluids. And we're going to first get the matter of discharge, what that is, and velocity out of the way. Now, if we have a pipeline, for instance, and we consider that the volume of liquid passing a given cross-section per unit time is called discharge. Okay, we could also call it rate of flow if we preferred. Now we normally denote it with the letter Q, and here's the part that might be strange to you, and that is that we have the units cubic meters per second. Now what's strange about that perhaps to you is the fact that a cubic meter of volume is a fairly large volume for normal everyday use, and seconds are a relatively short space of time. So what that's going to mean is that you might be dealing with very small numbers a lot of the time, because we would have very few cubic meters passing in 1 second for many small applications. But that's just something in engineering we've got to get used to. We often deal with very large numbers and very small numbers. But the reason for using these units, they are after all the base SI units for volume and time. So we really have no option but to use this unit of cubic meters per second for discharge. The next concept to consider is the velocity of flow in that pipeline we were talking about. And here's where we use mean velocity. And the reason for that is the velocity differs in the pipeline depending on whether you are near the walls of the pipe or whether you are in the center. In the center it is moving the most quickly, and at the walls it is effectively zero. So we have to work with what is basically an average velocity. So we call that the mean velocity, and that is going to be measured in meters per second, which makes sense. Base SI unit for distance is meters, and once again base SI unit for time is seconds. So now we have the situation where we have Q equal to V times A. Discharge is equal to average velocity or mean velocity times cross-sectional area. So if we had our pipeline, and our pipeline was like the one below here perhaps, and we knew what the average velocity was in that pipeline, and we multiplied that by the cross-sectional area, and if it's a round pipeline it would be pi upon 4d squared. If we multiplied those two, the product would give us discharge, and remember the units would be cubic meters per second. So you need to be completely comfortable with this calculation here. Now if we have a system where the cross-sectional area changes, for instance where we have pipes of different diameters in series, such as the situation over here, we have a large diameter pipe and a smaller diameter pipe, and some sort of connection, a tapering connection between the two. Now bearing in mind that whatever liquid was traveling along here had to be the very same liquid traveling along here a few instants later. In other words, in simple terms, what goes in must come out. And for incompressible flow, which is what we are going to be dealing with, certainly at the velocities and densities etc. that we are dealing with, we are certainly not going to consider any compression of the liquid. So we are dealing with what's known as incompressible flow at constant density. So we're going to say that the density of the liquid here is identical to the density of the liquid there, and if that is true for a tapering pipe, Q here would have to be identical to Q there. In other words, Q1 is the same as Q2, and let's remember that Q is equal to VA, so V1A1 is equal to V2A2, and this is the tool that you use for solving for an unknown in a tapering pipe situation such as this. If on the other hand we have a branching pipeline system where one pipeline splits into two, such as is the case here, once again what goes in must be what comes out. So in other words, the addition of Q2 and Q3 must be equal to Q1. What went in came out collectively. So Q1 is equal to Q2 plus Q3, and Q is after all equal to VA, so V1A1 equals V2A2 plus V3A3. So nice and simple concept, but you must be completely comfortable with those two scenarios. Next, we're going to look at a simple example, example 1, where we have a dashpot. I'll show you in a moment by means of a sketch what that is. It consists of a 46mm diameter piston fitting loosely inside a 50mm internal diameter cylinder filled with water. When the piston moves at 0.075 meters per second inside the cylinder, determine the average velocity of flow through the gap between the piston and cylinder. Right, now here's our dashpot. There is a piston. It is round in cross section. In other words, if you viewed it from below and you looked up, you would see a round piston, and it fits in a similarly round cylinder. Here are the walls. But there is a gap around the outside of the piston. And the purpose of the dashpot is to damp mechanical movement. So in other words, if you press down over here, this piston will tend to move downwards in the water, but there is going to have to be water displaced, and that water is going to race past the outside of the piston, and in so doing you are going to get a damping effect. You find dashpots in many mechanical installations. Probably the simplest is a door opening device, a dampener for a normal household door. If you wish the door to open slowly, you sometimes have a spring against damper setup. They wouldn't use water, they would probably use oil. But inside that setup, you have a slowing effect on the mechanical device, and that is caused by a dashpot. In this example, we have to find the average velocity of flow through the gap between the piston and the cylinder. In other words, how fast is the liquid passing by the outside of the piston. So to do that, I've considered 1 second, and I'm looking at how much volume is displaced as this piston goes downwards into the water. Now, as it goes downwards into the water, if we were to take its cross-sectional area at pi over 4 d squared, remember its diameter was 50 millimeters, and we multiply that by the 75 millimeters that it would move in 1 second. Remember, we were told that it was moving at 0.075 meters per second, and I've considered 1 second, therefore it's going to move 0.075 meters. So in moving 0.075 meters, this much liquid would have to have been displaced, and once again we are dealing with a very small number, and the way to handle that very small number efficiently is to use exponential terms. So we've got 147.262 times 10 to the minus 6 cubic meters. And it is a very small number. Don't be tempted to write down 0.000, many zeros, because you are more than likely going to be tempted to lose some accuracy and discard some digits. Rather use exponential notation for maximum accuracy. Anyway, that is the volume that is going to need to pass through this gap around the piston, in other words, in 1 second. So that volume passes through what is essentially an annular gap. That is the name given to this shape, because if we were to look at this from above, we would see 2 circles, a 50 millimeter circle and the bigger one, which is the inside of the cylinder. And the shape we are dealing with is this shape over here, and that is called an annulus. So it is an annular gap that the liquid is passing through. The area of an annulus is pi over 4 outside diameter squared minus inside diameter squared. And we have 50 millimeters and 46 millimeters that was given to us. So there we go. We now have the area, the cross-sectional area that this volume must pass through in 1 second, and we know that Q equals VA, so we can make V the subject of the equation, and we can end up with Q over A. There is our Q, our discharge. Remember, those units would be cubic meters per second, divided by the area that they must pass through, that would be meters squared, and you would be left with the velocity in meters per second. And there is your answer. That is the average velocity of flow through the gap around the piston in this example. Next up, we have a branching pipeline example. We are told a pipeline with diameter 450 millimeters and average velocity 1.8 meters per second reduces in size gradually to 300 millimeters diameter. So it went from 450 to 300 before branching into two pipelines of 150 diameter and 225 diameter. If the average velocity in the 225 diameter pipe is 3.6 meters per second, what will be the flow rate in the three pipelines and the average velocity in the 150 millimeter diameter pipeline? So here's what we know. A diameter 450 pipeline reducing gradually down to diameter 300 and then immediately branching into two pipelines, one of 150 diameter and one of 225 diameter. And only the velocity in the 225 diameter pipeline do we know. We don't know that velocity and we don't know this velocity. I believe we are asked for all of that. We are also asked for the flow rate in all three pipelines. Now, for continuity of flow, what goes in must come out, as we said earlier. In other words, QA, the discharge passing point A, is equal to the discharge passing points C and D added together. So because Q equals VA, it follows that VA AA is equal to VC AC plus VD AD. Right, let's see what we know out of all of that. We do know this velocity, by the way, VA at 1.8 meters per second. We do know the cross-sectional area at A, pi over 4 d squared. The d was 450 millimeters. And then at C, we don't know the velocity, but we do know the cross-sectional area. And at D, we do know the cross-sectional area and we do know the velocity. So if we stand back and look at this, we thankfully only have one unknown, which we can then solve for. And we find that the velocity at point C turns out to be 8.1 meters per second. So now we have all the velocities, and hence we can find all the rates of discharge for all the pipelines exactly as asked for. And then we can do a little cross-check at the end to check that in fact QA is equal to QC plus QD, which would just verify that we haven't made a silly mistake somewhere. So is this equal to that plus that? And yes, it would certainly appear to be. Example 3 is another branching pipeline problem where we have a 100 millimeter diameter supply pipe, that's this one here, and it branches into three pipelines of reducing diameter, 75, 50 and 40 millimeters. And what we do know is the total usage of the system is 54,000 liters per hour, so that's what's coming in here. Calculate the average velocity of flow in pipe B as well as the discharge in each of the three branching pipelines. All diameters are internal pipe diameters. So we know this velocity, this mean velocity, and this mean velocity. This one we don't know. The discharge is given in liters per hour. We must get right back to base SI units as fast as we can. In other words, we must get to cubic meters per second. So 54,000 liters is 54 cubic meters, but we're still per hour. So we divide by 3,600 because there are that many seconds in an hour, and now we would be back to cubic meters per second, and it turns out to be 0.015 cubic meters per second, the total discharge entering the system at that point. Now for pipelines C and D, we know the velocities and we also know the cross-sectional area. So therefore we know the discharge because Q is VA. So the V of this pipeline is 3 meters per second multiplied by the cross-sectional area at pi over 4 d squared would give us that much discharge in pipeline D. And similarly in pipeline C, that would be the discharge. Now because what goes in must come out, as we said earlier, this is what went in, and what comes out is that plus that plus that, two of which we know, one we don't know, so obviously we can then solve for it. So the discharge through pipeline B then must be 7.3 times 10 to the minus 3 cubic meters per second. How fast will the flow be in that particular pipe? Well, Q is VA, so V is Q over A. There's the Q, there's the cross-sectional area. So the mean velocity of flow in pipeline B is 1.653 meters per second. Next up we come to Bernoulli's theorem, and this theorem basically deals with the fluid system, just like any mechanical system, where energy at any 2 points in the system has to be accounted for in the way that it basically has to add up. The energy that was present at an earlier point in the system is identical to the energy of the same fluid once it reaches another point in the system. So in words, that means that the total energy of each particle of a body of fluid is the same, provided that no energy enters or leaves the system at any point. The division of this energy between potential, pressure energy and kinetic energy may vary, but the total remains constant. That's important. To account for energy leaving the system, losses, these are accounted for as we'll see in a moment. So I'm going to refer to before and after, simply meaning an earlier point in the system as before and a later point in the system as after. And losses are going to be accounted for as follows. The energy before is equal to the energy after, plus any losses that occurred along the way. So 1 is going to stand for before, 2 is going to stand for after. So if it was a pipeline system, for example, 1 would be an earlier point in the piping system and 2 would be a later point in the piping system, where that same matter, that same particle of liquid passed through. Now in mechanical systems, we normally dealt with potential energy and kinetic energy only, but in this fluid system we need to add in energy that could be stored as pressure. Now we'll work per unit weight, and the energy is therefore joules, which is after all what energy is measured in, per Newton weight of the liquid that we are dealing with. And in a very simplistic way, we can consider joules as work done, force times distance, and beneath the line we would have the newtons, because we are working per unit weight, and we therefore end up with a term in meters. And that conveniently is a way, as you may recall, how we expressed head in meters. And that boils down to the fact that we can simply work with meters head for all three of these terms. This will become clearer, I hope, during the first example, where we're going to show you how we are using meters for all of these three different terms. Even the losses will be expressed in meters head of that fluid. Now, before we dive into a problem, let's get this matter of losses out of the way. And I've provided you with this sketch which summarizes the various types of losses that we are going to deal with in fluid systems. And we are calling it energy losses in pipelines. And we are going to have two types of losses, shock losses and friction losses. Now, a friction loss is the loss of energy when liquid is moving in a pipeline and is coming into contact with the walls of that pipeline. It stands to reason that there is surface roughness on the inside of the pipe, and that is going to account for a loss of energy. And that is how we deal with friction losses. More about that in a moment. The other one is shock losses. When you have sharp changes in cross-section in a pipeline, there are also losses, because the liquid has to suddenly go from, in this example here for instance, from a smaller diameter pipe to a larger diameter pipe. And instead of having a nice smooth transition, if we have an abrupt change, we would have a shock loss, because the liquid molecules must suddenly change direction. That takes energy, and we have a small loss known as a shock loss. And we are going to deal with four shock losses. Reservoir to pipe is going to be that one. Pipe enlargement is going to be that one. Pipe reduction or contraction is going to be this one. And finally, pipe to reservoir, we're going to have this one here. So essentially we're going to have 4 types of shock losses for the purposes of our course, and a friction loss, which is measured or calculated rather using either the Darcy formula or the Chesi formula. The variables are here. Now, probably the most efficient way of showing how we apply these various losses is by means of a simple example where you'll immediately see how we apply them into the setup. Let's start with this one. A reservoir delivers water to a point 30 meters below it via a series pipeline consisting of a 400 diameter pipe, 600 meters long, connected to a 250 diameter pipe for a further 600 meters to the discharge point. Friction coefficient for the pipes, 0.004. That, by the way, is the F value in the Darcy formula. There it is there. It depends on the surface roughness of the pipe that you are dealing with. And the larger one has an F of 0.006. We must neglect shock losses for this particular example, so we won't use any of those for this first example, and consider only frictional loss to determine the rate of discharge. So here's the setup. There's the reservoir, there's the first pipeline, there's the second pipeline. I've drawn in all the parameters that we know next to the various pipelines: length 600 meters, diameter 400, friction coefficient 0.004. The next one was equally long at 600 meters. It was smaller diameter at 250, and the friction coefficient was slightly higher at 0.006, meaning that the walls of the pipe were slightly rougher. These 2 values, by the way, you would normally get from the pipe supplier, the manufacturer of the piping that you are using. Now we need to apply the Bernoulli equation, and the very first thing is to decide between which 2 points are we going to apply Bernoulli. Now, it stands to reason that we must apply it between a point where we want to know certain things and another point where we do know certain things. That would give us the least number of unknowns in our equation, and I've chosen point 1 and point 2. Point 1 is the top of the reservoir where there is effectively no motion, and point 2 is where the liquid has discharged from the last pipeline and has now entered the atmosphere. Next thing is to say what our datum level is, in other words, where we are making our measurements for height. So I'm going to make my lowest point in the system the datum, which will yield all positive numbers for height, which is a good thing. And finally, we are stating what type of pressure measurement we are dealing with. You may recall from the previous section of work, we either worked with gauge pressure or absolute pressure. I have elected to work with gauge pressure. So my heading is Bernoulli, point 1 to point 2. 2 is my datum, and gauge pressure is my system of measurement. Right, so if 2 is our datum, Z1 would be 30 meters, quite simply because point 1 is 30 meters higher than point 2. Then we move to the next 2 terms applicable to point 1. First is the pressure. Now, pressure at 1 is atmospheric, which is 0 gauge. So that's a 0, which makes the whole term 0. Velocity at 1 is effectively 0 because a water molecule sitting on the surface of the reservoir at that point would not be moving left or right. And yes, it would be descending very, very slowly, but because it's considered a large reservoir, we're going to assume that to be nothing, and therefore the velocity at 1 is also 0, making the whole term 0. Then we cross the equal sign and we get to the other side where we have Z2, which is down here at datum, so it is 0. Pressure 2, remember the liquid has exited the pipe and is now in the atmosphere, so it is also at 0 gauge. The velocity is not 0 at that point. It is most definitely coming out of the pipeline with a certain velocity. We'll call that velocity 2. It must be squared divided by 2g. 2g is 19.62, so that is the term here. Now we get to the 2 losses, and remember we're not doing shock on this one, we are only doing friction loss in this pipeline and friction loss in that pipeline.
It's 13 hours.
There's the Darcy formula. for the first pipeline and the Darcy formula for the second pipeline. Losses are always added to the side with the 2's, the after. So there they are, there's the 2 friction losses. Variables in the Darcy formula: 4 is a constant, 4 times F, there's the friction coefficient, L is the length of the pipeline, times V squared, the velocity, whatever it is, the mean velocity in that particular piece of pipeline, over 2 times the diameter times G. Likewise for the second one. And we then take it as far as we can, and we find we have 3 unknowns, which would normally present a problem to us. But then we consider continuity of flow, and we remember that what goes in must come out. So Q in the first pipeline must be identical to Q in the second pipeline, because after all they're in series, and what goes in comes out. And if Q equals Q, VA equals VA, and we can therefore get VA in terms of V2, which now leaves us with one unknown, which we can therefore solve for, and V2 comes out at just over 3 meters per second, and just discharge would therefore be that velocity times the area of the pipe at 2, which was 250 diameter, so there would be the area, and you get the answer of 0.151 cubic meters per second. So in summary, despite having a 30-meter head, we only attained that discharge, and that was primarily because of the friction in the pipelines. The only way to get a faster delivery of liquid would be to increase the head, and if that wasn't available or wasn't possible to us, we could consider increasing the diameter of the 2 pipelines, and that would immediately reduce the losses significantly and increase the discharge from the system. In the next problem, we have flow from one reservoir to another reservoir. So we don't have a pipe discharging into the atmosphere, and we are told that it is a 100 millimeter diameter pipe, the length is 30 meters, and we are given a few heights. All exits and entrances are sharp, meaning we must consider shock losses, and the friction coefficient in the pipe is 0.01. Calculate the expected discharge and the pressure at 0.3, which is halfway along the pipeline. And then make a neat sketch of the hydraulic gradient and the total energy overlaid on a sketch of the system. Right, what is a hydraulic gradient? Here's a hint. The hydraulic gradient is the height to which the fluid would rise in a standpipe connected to any point along the pipeline. Now, a standpipe would simply be a pipe that is connected to the pipeline that is open at the top. If you can figure out how high the liquid would rise in that pipe, you would have the hydraulic gradient heights for your system, and you could draw them on the drawing. Now I'm going to apply Bernoulli between 0.1 and 0.2, the surface of the liquid in the first reservoir and the surface of the liquid in the second reservoir. Now bear in mind, neither of those have motion, so we're going to conveniently have no velocity head at either of those points, and it's going to make matters quite easy. So 1 to 2 is our Bernoulli, and we're going to use gauge pressure. So as usual, the 1's are equal to the 2's plus the losses. Now the losses will be shock losses, entry to pipe, entry to reservoir, and of course friction loss. And I'm going to make the datum the lowest point, namely 0.2. And if you look at the sketch, 0.1 was 6 meters higher than 0.2, so that is Z1. Pressure at 1 is nothing because it's atmosphere and we're working in gauge. Velocity at 1 is nothing because it's standing still. And it's equal to height at 2, which is 0 because that's our datum level. This will be our datum level. And pressure at 2 is nothing in gauge because it is atmospheric. And velocity at 0.2 is also nothing because it's standing still. Then comes the first shock loss. You'll get that from that previous diagram where I gave you all the different losses. Then let's use Darcy for the friction portion, 4FLV squared over 2dg, and then the last remaining shock loss where it enters the last reservoir. And you're going to conveniently find that you only have one unknown, velocity, which you can then solve for. And once you have velocity, you can multiply it by cross-sectional area of the pipe and you can get the flow rate. Next up was to find the pressure at point 3, which was halfway along the pipeline. So to do that, we simply apply Bernoulli between two convenient points. And I'm going to go once again from 1 to point 3. Now point 3, remember, is midway along the pipeline, so it's over there. And once again, we can use 2 as the datum, so the 6 will stay, those 2 will still be 0. And at 3, we would have 0 for Z, because it happens to be at the exact same height as 2, which is the datum, if you look at the dimensions on the sketch. Now we get to the matter of energy in the water molecules as they pass through the system. Remember, a water molecule potentially started here at the surface. It found its way into the pipe, rather down here, it went down and it found its way into the next reservoir, and its energy changed all the time. It slowly reduced until it was stationary in the bottom reservoir. Remember also that its energy was made up of potential energy, pressure energy, and kinetic energy. So if we account for all of those by adding all three together, we can plot the energy of a water molecule as it goes down the system. So if we were to draw a separate graph, we would start with a graph that started up here somewhere, and we would find a sudden reduction for the first shock loss, a steady reduction all the way down for the friction that was being lost. That's supposed to be a straight line, and then another shock loss, and we would end up at the end. So in other words, our graph would look something like that. It would start up high over here, it would drop with a sudden drop as we had the shock loss of the reservoir to pipe, and then it would steadily reduce in a straight line as the friction energy was being taken off. It would then have a further shock loss, and it would stay at its low level at the bottom. So that would be the shape of the graph. Now conveniently, we might want to draw this graph on top of a scaled drawing of our actual layout. And because we express energy as meters head, we can, on a scale drawing, simply express energy as height above a certain datum level. So if this, for example, is our datum level, whatever height we draw above that is expressing the total energy of our water molecules. And that would mean that when they are at the start, they are at this height. So if I were to draw a graph on top of this scaled drawing, my graph would start out over here, and it would dip down, and then it would follow the path we mentioned earlier, which is a straight line, a descending path, as the friction energy is removed as the water makes its way down the pipeline. And then a further shock loss would occur, and we would end up at our finish point, which is level 2. And that would be the energy possessed. Remember, the energy is being drawn as a height above a certain datum. And if we were then at the datum, the energy would be 0. So to reiterate, the total energy curve or graph would look like this. That's our highest point, our most energy, a dip for the first shock loss, a steady linear reduction for our friction loss, a sharp dip for the final shock loss, and then we stay at our lowest point. So that would be the total energy curve or graph. Now comes the issue of hydraulic gradient. Hydraulic gradient is the height to which a standpipe would rise. So if in the pipeline at some arbitrary point such as this, we drilled a hole and we put in a pipe that was open to atmosphere on the top, while the system was running, liquid would rise into that pipe to a certain height. Hydraulic gradient is the height to which that liquid rises. So if this was all drawn to scale, and we had a real tapping into the pipe here and a real open-ended pipe that was vertical, and it was transparent and we could actually see the water rise, it would conveniently rise to a height that was exactly there. Now, when I say there, that point would be fractionally lower than the total energy curve. And the reason for that is the water that is in that standpipe is standing still. So it has been robbed of its velocity head. So this little piece that's missing, the difference, in other words, between the total energy curve and the height to which it rises in the standpipe, is one velocity head term, v squared over 2g. So a simple way of remembering it is the hydraulic gradient is simply lower than the total energy gradient by 1 v squared over 2g term. So knowing that, you can then draw in the hydraulic gradient as requested as a line parallel to the total energy curve, and it is simply lower by v squared over 2g. Right, now to practice that we've just been through, here is an example. Now I'd like you to stop the video and take a piece of paper and spend some time working out the solution before restarting the video and checking your solution. So here we have a large reservoir feeding water into a small reservoir, but in this case the pipe is open to atmosphere and the water falls the last little portion into the small reservoir. We are not to concern ourselves with any drop in level of the large reservoir, so we'll assume it's very large in comparison to the little one. So we're going to neglect any drop in the level, so we'll keep our level at where it is now. And we must find how long it will take in hours to fill the small reservoir, starting from empty, and then how long it would take if we replaced the 1-inch pipe with a 2-inch pipe, 25.4 to 50.8 millimeter. So as usual, stop the video and make a good attempt at this before looking at the solution, which will follow shortly. So there's the situation. I'm going to make B the datum. It's the lowest point in my system, which is a convenient place to use as a datum. I'm going to use gauge pressure, and I'm going to go Bernoulli A to B, A being a nice easy point where the liquid's not in motion, B being the point where the liquid has exited to atmosphere. So ZA plus PA over W, or specific weight, plus VA squared over 2G equals the B's plus the losses, which would be shock and friction. ZA is 5 meters. There it is. Nothing there, because pressure is 0 gauge, atmospheric, and velocity at the top here is nothing, it's standing still. Likewise, ZB, we are at datum, so there's no height there, that's 0. Pressure is atmospheric, which is 0 gauge, and velocity we need to consider. It'll be exiting with a certain velocity, which will be that number, squared over 2G, plus the first shock loss, which was reservoir to pipe, half V squared over 2G, plus the friction loss in the pipe along the way is 4 times F times L times V squared over 2dG. From that you can solve for V, and obviously once you know V, you multiply it by the area of the pipe, which was 25.4 diameter, and you get the answer in cubic meters per second. They wanted it in liters per second, so you can convert that. A cubic meter is 1,000 liters. So that's pretty easy. And then you've got to understand how to work out the time. We need 10,000 liters. That is the rate that we are getting the liters at. So it will take that many seconds. Divide by 3,600 to get it straight into hours, which was the requested unit for time, and we find 14¼ hours it will take. Then the question asked you to check how long it would take with a pipe of twice the diameter. So all of this stays the same, except now you're going to have to deal with a different set of parameters in the shock loss and the friction loss, and for that matter the velocity head. So you can solve for the velocity. It comes out to a higher number of 0.5434 meters per second, and hence a higher discharge. And now the time would be drastically reduced to 2.5 hours. So doubling the pipe diameter took the time to fill the reservoir from 14.25 hours to 2.5 hours. A significant change. Right, the next few problems come out of the Fluid Mechanics textbook by Douglas on page 183. We will be doing numbers 6, 7, 8, 9 and 16. There is number 6. Make sure that you understand the slope. They talk of the slope being 5.7 meters per kilometer. That is going to tell you the gradient of the pipeline and allow you to work out the relative heights between the various components. And similarly this one over here. So make a good attempt at drawing that and starting the problem before you carry on with the video and look at the solution. So that's what the drawing is going to look like. 5.7 meters per kilometer would mean a 9.12 meter drop for this portion and a 6.08 meter drop for this portion. So those two are added to the 6 meters that this pipe is below that first water surface, and you are then able to complete the sketch, including of course the 3.6 meters that was mentioned over there. So now you are in a position to carry on because you have all the dimensions. Next step is to draw, or rather to apply Bernoulli, and I'm going to go between 1 and 2. We've discussed before why that was convenient, and we're going to then consider the total Z, of course using 2 as the datum, which is my lowest point, and gauge pressure. So we're going to start off with Z1 at 17.16 meters, 17.6 meters, which is the height of 1 above my chosen datum. There it goes there. 0 pressure, 0 velocity at 1 because we are at atmospheric and we are not moving. And then Z2, which is at datum, so it's 0 height plus no pressure, we're at atmospheric, plus no movement, so we're at 0 velocity head. Then friction for the first pipeline and friction for the second pipeline. And fortunately we are told to ignore losses other than friction, so we don't have to worry about the shock at the 3 points. So you'll see that doesn't feature, just the friction losses. And that's going to allow us to solve for the velocity once we have figured out that velocity A relates to velocity B by the continuity of flow formula. Remember that Q equals VA, and what goes in comes out, so VA in the one pipe is VA in the other pipe. So we can get VA in terms of VB. In fact, VA turns out to be 2.25 times VB, and that's going to reduce our two unknowns down to 1 and allow us to find VB and hence VA. Once we have that, we can find the required discharge. Turns out to be 0.0163 cubic meters per second. Next up is the hydraulic gradient, and as we've discussed before, the hydraulic gradient is the height to which the liquid would rise in an open standpipe connected to various points along the pipeline, and that height would be different to the total energy by one velocity head term. Now the velocity head term differs in this portion to this portion because the velocities are different. So there's the one term, there's the other term. So that would be the offset vertically between the hydraulic gradient line and the total energy line. Now our total energy starts at liquid level. In this case, it does not drop because we are neglecting shock losses, so it goes straight into a line which descends at the gradient appropriate to the friction loss. There is not a dip because we are not considering shock loss here, so we continue straight into the next line at a different gradient and we end up at water level. No shock loss here either, so we go straight in at water level. Then we simply offset the hydraulic gradient line by the various velocity heads as mentioned before, and we end up with a line parallel to the total energy and a line parallel to the total energy. We then just join those two dots there and we have our hydraulic gradient line. And number 7, once again, stop the video, practice it, and then look at the solution once you've made a good attempt. There should be no problems with this one. It's very similar to what we've done, except that we must consider shock losses, because they say that both pipe ends are sharp and the loss at the entrance may be taken as that much. They're telling you one of the losses at the outset. So Bernoulli 1 to 2, surface to surface, using gauge pressure, and 2 as the datum. 1, 2, given shock loss, friction shock loss, and final shock loss. 6 meters is the height of 1 above datum. Those are both 0, as we've discussed a number of times before. Those 3 are all 0. Then the first shock loss, the friction loss, and the other shock loss. And you can then solve for velocity from that at 2.953. Then the corresponding discharge would be 0.02319 cubic meters per second, or that many liters per second. Then, as before, we had to find the pressure head in the pipe midway along its length. So we pick a spot midway along its length. We call that 0.3. We still use 2 as the datum, and much the same as before, except that at 0.3 the liquid is not standing still. It does possess a velocity head, so there it is there. And we have losses as well, only one shock loss between 1 and 3, and the friction loss for the portion of pipe in question, which is now shorter than before. And we find that the pressure at 3 is that many pascals, which relates to head of water as 2.67. You'll notice that this problem is very much like the earlier example 5. It was just expressed in a slightly different way. Right, in number 8 we have water flowing from a reservoir through a smaller diameter pipe, then into a larger diameter pipe. We must consider all the shock losses, all the friction losses, and determine the discharge. And we must give the answer in cubic decimeters per second. We are given the friction coefficient at 0.005 for both pipes. As you may recall from a previous few examples, we would get stuck with 2 unknowns because of the 2 velocities. So it might be smart to get the one in terms of the other one right at the outset, and this you do by continuity of flow. Q in this pipe is the same as Q in that pipe, so VA equals VA, and then you can figure out that the one velocity is 2.25 times the other velocity. So in the small pipe, flow is happening 2.25 times faster than the big pipe. Or you could express it this way around, the inverse thereof, if you wished. But once you have that, then you can work throughout with one velocity and come up with a tabulated form of all the friction and shock losses if you wish. That's what I chose to do here. I expressed shock loss in terms of V1. I expressed friction in terms of V1, and then I did the enlargement and I put it in terms of V1. Friction for the second pipe would initially have been in terms of V2, but then I replaced the V2 with 0.444 V1 and ended up with an answer still in terms of V1, which allowed me to add all of these together and get a total loss value in terms of V1. Then off to Bernoulli, and we do it in the normal fashion, but then when it came to adding losses, I could simply use the total value. There it is there, which might be a quicker way of doing it. You can then shortly thereafter solve for V1 and of course get Q, because Q is VA, and they wanted the discharge expressed in cubic decimeters per second. Now a cubic decimeter is actually just a liter, because there are 1,000 cubic decimeters in a cubic meter, which means it's actually just a liter. So you can express your answer appropriately. In number 9, we have a series pipeline system again connecting two reservoirs, and we are asked to work out the actual head loss at each point in meters, which is slightly different to previously. And we start off by working out the loss of head at the entrance to the pipe, which we know to be half V squared over 2G. And we also know that the velocity of water in the smaller pipe is 1.2 meters per second. So straight away we know that velocity, so we can immediately get that loss expressed as meters head of the water. Then at the junction we have the formula for enlargement of pipe, and to be able to work that out we need the other velocity. Now the other velocity in the other pipe we can work out using continuity of flow. By knowing it to be 1.2 meters per second in this pipe, we can find it to be a little bit less in this pipe by the ratio of the areas. Because remember that Q equals Q, so VA equals VA, and when you have the areas one upon the other, the pi over 4's cancel out and you simply end up with diameters squared. So you can find the ratio between the two velocities, and you find that the velocity in the bigger pipe is a lot less than the velocity in the smaller pipe, which stands to reason. Once you know that, you can put the two velocities into the formula and get the actual head lost in meters. And finally, you must find the shock loss at entrance to the lower reservoir, which is V squared over 2G, and there you get your answer. And then there's the two friction losses, which you can work out using Darcy for FL V squared over 2dg. There's the first one, there's the second one. And now you can simply add all of these losses together and get a total loss. Now to find the difference in levels between the two reservoirs, we're going to use Bernoulli in the normal fashion. And we have A's on this side, B's on that side, and of course losses over there. Now the losses are conveniently already worked out for us. I've rounded it off to 1.09. And amazingly, there are a bunch of zeros, and the difference in level happens to be 1.09, which stands to reason, because we were going from a point with no flow and atmospheric pressure to a point with no flow and atmospheric pressure. So the difference in level had to be the total head loss, which is after all 1.09. In our last one, we look at a parallel pipe system. The only difference between the two parallel pipes is the fact that one is a lot longer than the other one. So one took a longer route than the other one, hence it is 3 kilometers long versus 1.5 kilometers long for the other one. They're also different diameters. And we must find the discharge from the larger when the smaller is delivering that discharge there. So if the smaller is delivering that discharge, we can find the velocity in it. And knowing that, we can now apply Bernoulli to just pipe 1, A to B. And we find that the difference in height between the reservoirs must be 5.163 meters to achieve said flow rate. And now that you know that, you can go straight into pipe 2 and find its velocity of flow by applying Bernoulli between its two points A and B, now that you know this difference in height, because obviously it's applicable to both. So you soon find the velocity in pipe 2, and hence with Q equal to VA you can find the discharge in that pipe too.